All right, hello. Welcome to Project 2 for mechanics. Today I will be attempting to model a three-body system of the Sun, the Earth, and the Moon. Now, to begin with, I'm going to have to import all of these functions. I used a matplotlib to do a 3D plotting of these functions. Let's see. So we have a heliocentric model created in 1543 by Nicholas Copernicus. And to do that, we're going to, well, at least to do this on this computer, we're going to need it to make a few assumptions and a few approximations. One of those assumptions and approximations to get this thing to actually work is to make the masses a little less celestial. And this is honestly, I fiddled with some numbers beforehand, and this was kind of the tightest I could get it without the system completely breaking. But either way, we have our three masses for the sun, which which is apparently 33 mass units large, and the Earth, which is 10, and the Moon, which is 5. And then now we create an array for our positions. So we have our X position, our Y position, our Z position, and then the same for our velocity. We have our velocity, Y velocity, and Z velocity. And then we have each of those for the mass 1, the mass 2, and the mass 3. Let's do that. And so as you can see here, our mass 2 is the Earth, and our Earth is going to be the center of our model right now, which is a little bit counterintuitive to the heliocentric model, but it works for experimentation purposes. So what we can, once we have all of our initialization set up, we can define acceleration. So to get our position function, we obviously have to do x naught plus v naught t plus mgt squared. We do the manual derivative of that. We get v naught plus 2 mgt. And then the derivative of v would be dv or v dot. We get mg dx dt ddt because we can take our t and then we do the dv dx and then we do dt dx and then we can turn the dt dx into dx dt ddt and we can move the ddt out into our actual calculation function down here. This is just the acceleration function. So we have m, and then we have g, and I have g is minus 9.8, and then we have to do the distance function for these because it's dx dt, and then we can do the manual distance function by having we do this for all three. We have position 1 and minus position 2, and then we have the script r. So it would be r divided by script r. So we have square root of the x p1, p2, the y p1, p2, and the z p1, p2, and then we square root that and cube that because there's three of them. And then we do the same thing for position 1 compared to position 3. So we need to do position 1 compared to position 2 and position 1 compared to position 3 for this planet 1 dv, and then we subtract one of those from the other because this is still negative. So and then if the velocity is negative, it would change this to a positive, and then they would have a negative um, correlation with you, not a correlation. They would cancel each other out, is what I'm trying to say. And then we do that for planet 2. It's the same function. We have the r over script r over script r. And we have planet 3 dv, and then once we do this, we initialize our time steps here. And I did a lot of steps. I basically pushed the little simulation as far as it could go so I could show as much clarity as I could. We initialized time is 0, and then the time step is like a millisecond. And then we have, I think this was 200,000 steps. And then we then initialize our P1 and V1, which is going to be, we're going to start at 0, 0, 0, 0, 0, 0 for each of these. And then once we have our our starts, we can put our starts into here a little bit right down here. We initialize it with 0, 0, 0 to begin with. Um, did I initialize this? Let me just do that again. Okay, and then we put the P1 start, P2 start, P3 start, V1, V2, V3 start into each of these. And then we have, I didn't really know if the lists were too particularly valuable of a resource. Because I mean, there's like 200,000 time steps. Like you can't see all these things, but I put them in because, it's, if I could make this larger, I would, but it contains all the data either way. But either way, we make the lists here from some of the earlier coding functions. And then for the range, which we're doing 20,000, 200,000 steps, we have our change velocity for each of these, and then we plug that back into the this acceleration function. And then what we do is we step up the velocity function. So we go from v0 to v1, and then we take assuming we're starting at v0, we take the initial velocity, which would be given by something up here. This would be -3, and then we do the acceleration function, and then that would spit out the change in velocity. So that would be the original velocity, and that would be the change of velocity times the time step. And so because the time step's so small and the change of velocity isn't going to be too big for each of these steps, but it will compound over time. And then we add that to the list right here. We do that for V2 and V3. And then the same thing for the position, because the position is just the initial position plus the change in velocity, which is change in position over time. And then we do delta t, and it would just be a change in position. Be a new position with this one. We append a list here, do the same thing here, and then for P3, we up the time scale, and then we append time list. We initialize that here. This is what takes the longest because when you do these three body problems, you have to uh, do this for 200,000 steps, a lot of delta time. So if you do the delta time times 200,000 steps, you should get about 2,000 seconds. So this thing is being modeled for 2,000 seconds. And then you could put the data from the simulation or the list we've collected in here. And again, it's there, but it's not the most helpful. I mean, you can see the starting positions and the ending positions where it starts at like -10 and then it ends 360, and then this starts at a velocity of -3, it ends at a velocity of -1, starts at 0, 0, 0, ends at 333, ends at -3 or -333, starts at 10, ends at 376, -376. And then this is the modeling function. I used matplot, and originally the matplot didn't work. I had to change this to a subplot, and then once I changed this to a subplot for the acceleration of this, it worked pretty well. But let me click this again so we can get a better view of it. And we plot our x in P1, our y in P1, our z in P1, same thing for 2, and the same thing for 3. And we have red for the sun, green for the earth, white for the moon. And let's see, when I was able to get rid of the axes on this, so it's just you can just see the starting functions and then how they basically devolve into chaos, which I probably could have attempted to model the distances between the Earth and the sun and the moon a little bit better. But whenever I attempted that, it all kind of just collapsed in on itself because the mass of the sun was very, very large as it is in real life, and they would basically just whatever direction the sun was going, the other two celestial bodies would just collapse in and follow. So, I mean, if I made this figure larger, it would crash the simulation. If I made the mass any larger, it would crash the simulation. And if I made the velocities any larger, it wouldn't crash simulation. It's just you wouldn't see anything because again, the this is about as large as I can get the figure size to go without crashing the simulation. Um, I attempted to do a animation, and that did not work very well. The animation would go for about 30 frames, and then it would crash because I have 200,000 steps. But I might be able to get the animation to work. The way it works right now is it spins the the figure Adam Musil direction depending on whatever the range is. With in this case, I put to 360, so it would spin in a circle as it's creating it, and it looks cool, but again, it crashes the simulation. So I just kind of gave up on it. I probably could get it to work, but not right now. But I think that is everything. Yeah, the simulated masses, nowhere near the real masses, simulated velocities and positions, um, manually calculating the change in velocity by using R and script R, and then G and mass, initializing the positions and velocities, doing the time steps, putting in the starting positions, velocities, starting these lists, um, and then manually changing velocity. We have the acceleration, the dv, times the delta t step to get us a change in velocity times delta t, which is a new velocity. For each of these, same thing with position, and then graphing this data here, and then putting that graph data into this plot right here for x, y, and z for each of these. Um, and then you end up with something like this, where you can see the sun and the earth kind of attempt to do some sort of stable rotation, and the moon just kind of goes off on its own because the velocity is very small. And if it's not extremely close to the earth, then it's not going to stay in an orbit. Funnily enough, the moon in real life is slowly getting farther away from Earth. I don't know the exact time frame, but eventually, this might be wrong science, but from what I've read so far, that the moon is eventually going to leave the orbit of Earth in I don't know the time step, but maybe it was however many million years. But either way, I think that is everything I have to say about this coding function. Thank you for watching, and how do I turn this off?